Good afternoon, everyone. My name is Gauri Vaidya, and today I'll present our research on PurGE towards responsible artificial intelligence through sustainable hyperparameter optimization. This work addresses the inefficiency in hyperparameter tuning, a process that is computationally expensive and environmentally costly. Our method, we name it as PurGE, makes hyperparameter tuning more efficient, faster, and environmentally sustainable. Let's begin by understanding the problem. Hyperparameter tuning is like baking a cookie. You need the right balance of ingredients to get the perfect result. Similarly, in machine learning and deep learning model, we have to find the right settings by searching before even we begin the training. That search process is quite expensive as well as time consuming, and that's the problem we aim to solve. Here is one example which shows the effect of learning rate and batch size on validation accuracy of the model. As we can see, it's quite crucial to get the right settings as it directly impacts the model performance. So, in general, hyperparameter tuning for machine learning or deep learning model works like this. We start with a given model, a dataset, and a set of hyperparameters. A budget is assigned, usually in the form of trials, and the configurations are tuned based on some predefined logic. The tuning process continues, testing different configurations until either the budget runs out or we find the best possible hyperparameter settings. Now, because the models have so many different hyperparameters, tuning takes a huge amount of time and also the computational resources. And when we are working with deep learning models, the cost of this tuning grows exponentially. Beyond computation time, there's another major problem that's about energy consumption. Training machine learning model has a huge carbon footprint. For instance, optimizing a natural language processing model can produce over 78,000 pounds of carbon dioxide, which is as same as driving a car for 5 years. On the other hand, neural network architecture search, which is a technique used to design deep learning models, is even worse. It generates over 600,000 pounds of carbon dioxide, which is equivalent to 300,000 pounds of coal. So, to summarize the motivation, hyperparameter tuning is not just an efficiency problem, but it's also an environmental one. So, moving towards responsible AI, we need optimization method that reduce computational efforts while still delivering strong performance. And that is exactly what PurGE does. PurGE improves hyperparameter tuning in three key ways. First, it prunes the hyperparameter search space, that is, it discards the evaluations with weak configurations. Secondly, it balances the exploration and exploitation, so we efficiently find the best hyperparameters. And third, it reduces the computational efforts, cutting trials by up to 35% and making tuning up to 47 times faster than standard approaches. We'll see the results in more details after we discuss in the experimental results. Now, let's take a look at how exactly PurGE works. So, in the traditional hyperparameter pipeline, we propose to use grammatical evolution as the optimizer. So, grammatical evolution is an evolutionary algorithm that follows Darwin's principle of natural selection, that is, only the fittest survive and evolve. The process begins with a population of different hyperparameter settings. The best performing candidates, based on the validation accuracy, are combined and also mutated to generate new candidates. This cycle continues until the termination criteria are satisfied, progressively refining the search. What makes GE unique is the structured grammar, which provides the flexibility to handle hyperparameters across different frameworks and architectures, ensuring a more adaptable and efficient tuning process. The second modification that PurGE does in the pipeline is dividing the budget in two phases. In stage 1, PurGE explores the search space and identifies the poorly performing configurations. Instead of evaluating every possible option, it discards these low performing candidates. It also captures the correlation between hyperparameters, ensuring that the search remains focused on the most promising regions of the space. So here is the overall framework of PurGE. Now let's take a look at an example of how exactly PurGE works at backend. So we begin with a search space of 103,000 configurations covering 6 key hyperparameters, that is batch size, optimizer, learning rate, momentum, dropout, and the number of layers. The goal is to maximize the validation accuracy while reducing the number of trials. Now PurGE operates in 2 stages. Stage 1 will run for 60% of the total trials and will focus completely on exploration. The first step is to eliminate the weak candidates, and so therefore any configuration with validation accuracy below 50% is discarded. From here, PurGE computes the correlation between remaining hyperparameters to identify the patterns in the search space. So here is a heat map which shows a model tuned for CIFAR10 dataset. What we can see from the graph is there is a strong correlation between batch size, optimizer, and momentum with validation accuracy. Now, when we further analyze these with individual condition expectation plots, we can observe from the optimizer plot that SGD is having a strong negative dependence on the validation accuracy. And therefore, we can safely discard SGD and just keep ADAM and RMS prop in the hyperparameter search space. Similarly, we also obtain the optimal performing regions for momentum as well as batch size. Additionally, the correlation heat map also gives the hyperparameters pairs such as optimizer and momentum, learning rate and dropout, and momentum and layers. These correlations help refine the search space by narrowing down to the most promising configurations. From here, PurGE will further define these pairs, giving us the most promising configurations. Now, this results in just 72 unique configurations, a 90% reduction in the original search space, making it significantly efficient. Now, in stage 2, the remaining 32 trials are dedicated to fine-tuning the best configurations. The optimal hyperparameter setting is then selected based on the highest validation accuracy, and we train the model. So with this two-stage approach, PurGE achieves explainable and efficient hyperparameter tuning, reducing the search space while also retaining interpretability. So in our study, we focused on 2 key research questions. First, how does pruning the search space and models impact the performance of hyperparameter optimization? And second, how does pruning the search space and models affect resource utilization during hyperparameter optimization? To answer these questions, we conducted experiments across multiple datasets. So we tested PurGE on both tabular and image datasets. So for tabular data, we used segment, waveform, and bank datasets with XGBoost, while for image datasets, we tested CIFAR10 and CIFAR100 using EfficientNet 7 and ResNet 50. We compared PurGE against random search, grid search, and Bayesian optimization using tree structured Parson estimator, which I am going to further call now as TPE. This is a Bayesian optimization method which also follows a structured approach with using trees. Now, further, we'll look at more detailed experimental setup. So in the hyperparameter tuning phase, we only use 5% of the dataset to speed up the process. For neural network, the subset was trained over 5 epochs, while for machine learning model, that is XGBoost, the same subset was trained using the entire XGBoost model. After tuning, when we move towards the final training stage, the full dataset was used for training over 40 epochs. The dataset was split into 60% for training, 20% for testing, and 20% for validation. On the right, we can see the key parameters used in the grammatical evolution search. The budget or trials, as we call it, is the product of population size and the total number of generations. So in our case, the population size is 10, and for stage 1, the generations are 5, and for stage 2, the generations are 3. This gives the budget of total 80 trials. So moving on to results, answering the first research question, the test accuracy of the final models trained using PurGE was comparable to traditional approaches. Now, since the accuracy remained similar, we focused more on comparing the number of trials obtained by each of the methods. Here is a graph showing the budget used by traditional approaches versus PurGE. As we can see, PurGE consistently required fewer trials across all the datasets. On an average, the number of trials is reduced by 28 to 35%. This reduction is strongly due to the evolutionary approach used in PurGE, as we believe. Instead of blindly searching, PurGE allows candidates to optimize and evolve simultaneously, making the tuning process efficient. We also further analyzed how different tuning methods explore the search space. Here, we have violin plots comparing random search, grid search, TPE, and PurGE, showing how each method distributes trials across the search space. The plots present both stage 1 and stage 2 of PurGE. What we observe in stage 1 is stage 1 focuses more on exploration, covering a wider range, whereas stage 2 focuses on exploitation, refining the best performing configurations found in stage 1. This structured approach ensures a balance between exploration and exploitation, which exactly was our aim. A similar pattern is observed across all the datasets, which further validates our claim. We also conducted a Mann-Whitney U-test with 95% confidence interval to statistically validate the differences between the tuning processes. The results confirm that PurGE consistently outperforms random search and grid search across all datasets, whereas when compared to TPE, PurGE outperforms in 4 datasets out of 6. Now, moving on to research question 2, and specifically focusing on computational efficiency, PurGE provided significant improvements in execution time. This graph shows the execution time in minutes for each of the model dataset pair. So to summarize, for tabular dataset, PurGE achieved an average speedup of 47 times as compared to the baseline methods, whereas for image datasets, PurGE was twice as fast as traditional tuning approaches. The efficiency of PurGE can be directly translated into energy savings. So with an average of 30% reduction in trial and 47 times speedup, PurGE reduces carbon dioxide emissions by 2,384 pounds per optimization task. This is a significant reduction, an attempt from this research making hyperparameter tuning more responsible and sustainable. So to conclude, hyperparameter tuning is a fundamental part of machine learning and deep learning models, and PurGE is a step towards optimizing it responsibly and efficiently. By pruning low-performing regions in the search space, PurGE makes the tuning process faster, computationally feasible, and environmentally responsible. We also showed that it can reduce the trials by up to 35%, achieving a speedup of 47 times for tabular datasets and 2 times for image datasets, and also significantly reducing the energy consumptions. These improvements are not just about efficiency. They are about building AI that is responsible and sustainable. So as models grow more complex, efficient and responsible tuning is going to be a key, and PurGE is a step towards that. These are some of the key references. and I'll be happy to take any questions now. Thank you so much for your time.